We've seen how we can describe light using different models, each model more complicated and more complete than the preceding one. The simplest model is the ray model, which says that each object point scatters rays of light in all directions, and that each ray travels in a straight line. With this model, the pinhole camera can be explained. In the double-slit experiment, one can observe interference fringes, which cannot be explained using the ray model. Rather, to explain this phenomenon, we have to model light as a wave. Later we found that light has a property called polarization, which can be demonstrated using polarization filters. Depending on the orientation of the filter, different amounts of light can be transmitted. So we found that light is described using a vectorial wave equation. More specifically, it was found that light is an electromagnetic wave, and its wave equation can be derived from Maxwell's equations that govern electromagnetism. In classical physics, this is the most complete and accurate model of light. However, in the early 20th century, certain observations indicated that light comes in discrete energy packets, or quanta, which is not predicted by Maxwell's equations. One such observation comes from blackbody radiation. To accurately describe the radiation spectrum of a blackbody as a function of its temperature, it was assumed that this radiation is emitted or absorbed in discrete packets of energy. Another observation was the photoelectric effect. When shining light on a metal surface, electrons are emitted, and to explain the rate at which these electrons are emitted, it was assumed that light comes in discrete packets of energy, called photons. A third observation was Compton scattering. If light hits a particle from a certain direction, the light gets scattered in one direction, while at the same time getting a longer wavelength, and the particle recoils in another direction. The way the scattering occurs could be explained by assuming that light is quantized. So we have these two conflicting models of light, both well supported by experiment. One stating that light is an electromagnetic wave described by Maxwell's equations, the other stating that light acts more as a particle, coming in discrete packets of energy called quanta or photons. Naturally, the question arises, how do we reconcile these two models? The short answer would be quantum mechanics. We will elaborate on this answer in 4 parts. First, we need to understand how in quantum mechanics particles have a wave-like character. For example, an electron orbiting the nucleus of an atom isn't really like a planet orbiting the sun. Rather, it is described by a wave function that is present all around the nucleus. Next, we need to understand how we can assign observables to a particle if it is described by a wave function. More specifically, if we could imagine an electron as a point particle orbiting the nucleus, we could at each point in time assign it a position and a momentum. But if it is instead described as a wave function that is always spread out over space, then what would its position or momentum be? We will see that the position isn't a vector anymore, but an operator. And just like there is a position operator, there is also a momentum operator. Once we know how to describe the behavior of a particle using quantum mechanical theory, we will study a particle in a particular system, namely the harmonic oscillator. In a classical harmonic oscillator, the particle would oscillate the same way an electric field in an electromagnetic wave would oscillate. So once we know how to treat the harmonic oscillator quantum mechanically, we'll be able to quantize the electromagnetic field. Let's see how we can describe a particle as a wave. We can imagine some wave function psi of x that somehow describes the particle. In quantum mechanics, this wave function is typically denoted using special brackets. The reason we want to do this is to distinguish the physical object from a particular representation. For example, we can write down the wave function as a function of position, but we could also take the Fourier transform and write the same wave function as a function of spatial frequency. We're still describing the same particle and nothing physically changed, but we simply represent the same physical object in 2 different ways. As another example of how the same physical object can be represented in different ways, consider some vector. Currently, it's a physical object that exists, but we cannot yet represent it with some numbers. Once we choose a certain coordinate system, or basis vectors, we can express the vector in terms of these basis vectors. But if we choose a different coordinate system or different basis vectors, then we will use different numbers to represent the same physical object. More generally, we can describe it as follows. If we have 2 basis vectors, e1 and e2, then we can represent the vector psi by projecting it onto these basis vectors. So the first coefficient is given by the inner product of psi with e1, and the second coefficient is given by the inner product of psi with e2. We could write these inner products more explicitly by multiplying a row vector with a column vector. In quantum mechanics, the row vector is called a Brahe vector, and the column vector is called a ket vector, so that the inner product of the two vectors form a bracket. In the example we just saw, psi was a simple two-dimensional vector, but the same holds when psi is a function of a continuous variable. In this case, the position representation of psi is found by taking the inner product of psi with position basis vectors. This inner product can be written as an integral, where the basis vector for a position x is, in the position basis, given by a delta function that peaks at x. Similarly, the frequency representation is found by taking the inner product of psi with frequency basis vectors, where the basis vector for a spatial frequency fx is, in the position basis, given by a plane wave with period 1 over fx. In the frequency basis vectors would be given by delta functions. So we've seen how the same physical wave function can be represented in different ways by projecting the wave function onto different basis vectors. But the more important question is, if this wave function is supposed to represent a particle, then how do we assign particle-like observables, such as position and momentum, to a wave function? After all, a point particle has one certain position at a certain point in time, but a wave function can be spread out throughout space. What we can do is try to imagine what the wave function should look like if it were to have a definite position or definite momentum. A wave function with a definite position would have to be a delta function. If the delta function peaks at some position x0, then we could unambiguously say that the particle with that wave function has a position x0. So what would the wave function of a particle with definite momentum look like? According to the Broyes hypothesis, the momentum of a particle is related to its wavelength. A particle with wavelength lambda has a momentum of Planck's constant h divided by the wavelength. We can rewrite this expression in terms of the reduced Planck's constant h bar and the wave number. So a particle with definite momentum should have a definite wavelength, which means its wave function should be a plane wave, and its wave number is equal to its momentum divided by h bar. Note that this means that in quantum mechanics, a particle cannot have a definite position and momentum at the same time, because a wave function cannot simultaneously be a delta peak and a plane wave. We can now find how the momentum representation is related to the position representation of the wave function. By taking the inner product of the wave function with the momentum states, both in the position representation, we find that the momentum representation psi tilde of p is given by the Fourier transform of the position representation psi of x. Because the x and p representations are related by Fourier transform, these are called conjugate variables. So in general, a particle has a wave function that is spread out in both the position and momentum representation. But what does it mean for a wave function to have multiple positions and momenta? To answer that question, we have to consider the squared modulus of the wave function. Note that in terms of optics, if psi of x were an optical field, then the squared modulus of psi would be the intensity, which is what we would see or measure with a camera. If we sent an optical field through a double slit, then the intensity we would measure on the screen shows interference fringes. Now imagine that instead of light, we send electrons through the double slit. On the screen, we would detect the electrons one at a time at random but definite positions, since electrons are particles. However, if we collect electrons over a sufficiently long time, we will find that an interference pattern emerges. This is evidence that the electron, while it is a particle, also exhibits wave-like behavior. It also indicates how we should interpret the wave function. The squared modulus of the wave function describes a probability distribution according to which the electrons hit the screen. If we measure enough electrons, the probability distribution is revealed. This statistical interpretation of the wave function is called Born's rule. Also note that since modulus psi squared is a probability distribution, it must integrate to 1. In other words, the wave function must be normalized. Let's discuss another consequence of the probabilistic interpretation of the wave function. Let's say the position of the electron is described by the probability distribution modulus psi of x squared. Once we measure the position of the electron, one way or another, there is no uncertainty anymore in the position, and so the probability distribution must collapse, and accordingly, the wave function must collapse. As the wave function collapses to a delta function in the position representation, it must become a constant function in the momentum representation, which means that while the position is now completely certain, the momentum is now completely uncertain. So there is an uncertainty between position and momentum. If we know the position, then the momentum is uncertain and vice versa. We can then ask the question, can we quantify this uncertainty between position and momentum? Fundamentally, the uncertainty comes from the fact that the position and momentum representations are related by Fourier transform, and if in one domain you make the function narrower, then in the other domain the function becomes broader. We can quantify this relation using the variance, which is given by the square of the standard deviation, which is denoted by sigma. To calculate the variance in x, we multiply the squared distance from x to its mean value with the probability distribution of x, which we just saw is given by the squared modulus of psi of x. Similarly, we can write down the expression for the variance in p. Using the fact that psi of x and psi tilde of p are related by Fourier transform, one can derive the following relation between sigma x and sigma p. The product of the two must always be larger than or equal to h bar over 2. This mathematical result is referred to as the Kennard inequality, while its physical implications regarding position and momentum are known as Heisenberg's uncertainty principle. We have seen how we can describe a particle using a wave function, how this leads to uncertainties in position and momentum, and how these uncertainties are related. The next question is, how do we use these observables in calculations given that they have inherent uncertainties? For example, if we have a quadratic energy potential, which is proportional to x squared, what would it mean for a particle that doesn't have a definite x? Or, what if we want to calculate the kinetic energy, which is proportional to p squared? How would we do that if p is not well defined? Let's first look at the simplest case. What if we have a state with definite position x0 or a state with definite momentum p0? In this case, we can easily define the value for the position, which is x0, or the value for the momentum, which is p0. The values for the potential and kinetic energies are then also calculated straightforwardly by plugging the value of x0 or p0 in the expression for the potential or kinetic energy. Now let's suppose we have a state which is a superposition of two states with definite position x0 and x1, or a state which is the superposition of two states with definite momentum p0 and p1. What would be the position or the momentum of such a state? We cannot simply assign a single value to the position observable or a single value to the momentum observable. Rather, observables now become operators that can act on the wave function, and these operators are indicated with a hat. When you apply the x operator to the wave function, then the state with position x0 will get multiplied by x0, and the state with position x1 will get multiplied by x1. And the same goes for the momentum operator. By the same reasoning, the potential energy and kinetic energy now also become operators, and if you apply the potential energy operator to the wave function, then the state with position x0 will get multiplied by the potential energy at x0, etc. Let's now extend these results to arbitrary wave functions. If we have a wave function psi, we can represent it in the position basis by taking the inner product with states of definite position, or we can represent it in the momentum basis by taking the inner product with states of definite momentum. If we apply the position operator to psi, and then express the result in the position basis, then we have simply multiplied psi of x with psi, and similarly, applying the momentum operator corresponds to a multiplication with p when in the momentum basis. If we apply the potential energy operator to the wave function, then we multiply by v of x in the position basis, and if we apply the kinetic energy operator, then we multiply by t of p in the momentum basis. So we've seen how to define the potential and kinetic energy in quantum mechanics, namely as operators that act on a wave function. But now let's say we want to calculate the total energy, h, which is the sum of the potential and kinetic energy. Quantum mechanically, h becomes an operator that acts on a wave function psi, and we can express the result in the position basis by projecting it onto states with definite position. We can write h as the sum of v and t, and what we find then is that we need to apply t to psi in the position basis. Now we've already seen how to apply t in the momentum basis, but how do we apply it in the position basis? Or more fundamentally, how do we apply the momentum operator in the position basis? There are two ways to find the answer to this question. One way is to simply apply p in the momentum basis, and then express the result in the position basis by inverse Fourier transforming it. So let's write down the inverse Fourier transform of p times psi tilde of p. We can substitute the factor p with the derivative with respect to x, which can be taken out of the integral. The integral can then be expressed as psi of x, so we find that applying the momentum operator in the position basis means taking the derivative of the wave function. Let's write down the same calculation in a somewhat different notation to get a different perspective on what we've done. We wanted to apply the momentum operator to psi and express the result in the x basis. We found that this expression should be equal to an integral over all momenta of a momentum state expressed in the position basis multiplied by the momentum operator applied to psi expressed in the momentum basis. We can rewrite this expression by observing that we only integrate over p, and by comparing the left-hand side of the equation to the right-hand side of the equation, we conclude that this integral must be the identity operator. We can intuitively see why that must be the case by looking at a simple two-dimensional example. Let's say we apply this operator to a wave function psi, which is now a two-dimensional vector. The vectors e1 and e2 are orthogonal basis vectors. When applying the operator to psi, you compute the projections of psi onto the basis vectors, so you decompose psi into e1 and e2 components. Then you sum the components back together to find psi again. By changing the order of the symbols around, one can conveniently rewrite this procedure of decomposing psi into orthogonal components and adding them back together as a single operator, which is the identity operator since it does not change the wave function. So we saw that applying the momentum operator means taking the derivative in position space. Another way to find the same result is by considering the eigenvectors and eigenvalues of the momentum operator. Let's consider once more the case where the state has a definite position x0 or a definite momentum p0. We saw that when applying the position or momentum operator to such a state, the state is simply multiplied by the corresponding position or momentum value. In other words, if you have an operator that corresponds to a certain observable, then its eigenvectors correspond to the state with a definite value for that observable, and that value is given by the eigenvalue. So in the case of the momentum operator, we know that in the position basis the eigenvectors are given by plane waves, and the eigenvalues are p0. Indeed, these are also the eigenvectors and eigenvalues of the operator minus I h bar times the derivative with respect to x. So we saw that in the position representation, the position operator corresponds to a multiplication with x, and the momentum operator corresponds to taking the derivative. Using this result, we can make the following observation. If we first apply p and then x, we get something different than if we first apply x and then p. In other words, x and p do not commute. We can make a more precise statement by defining the commutator of x and p, which is the difference between xp and px. If we apply this operator to an arbitrary wave function psi, then we can write out the derivative using the product rule and cancel some terms to find that we've multiplied psi with a constant factor of I h bar. This result is known as the canonical commutation relation. Now let's get back to our original question. How do we calculate the total energy of a particle quantum mechanically? The classical expression for the total energy H, also called the Hamiltonian, is given by the potential energy plus the kinetic energy. In quantum mechanics, this Hamiltonian becomes an operator, and its expression in position space is found by substituting the momentum by the momentum operator, which is the derivative with respect to position. This means that the Hamiltonian contains a second derivative, or in the case of three-dimensional space, it contains the Laplace operator. So we have found the operator for the total energy. Remember the observation we made before. The states of definite energy are given by the eigenvectors of the energy operator, and the possible values of the energy are given by the eigenvalues of the energy operator. One could use this equation to calculate the energy levels of an electron in a hydrogen atom. Plug in the expression for the electrostatic potential energy, and then solve for the eigenvalues and eigenvectors. This procedure correctly predicts the observed energy levels up to a certain degree of accuracy, which is further evidence that this is indeed the correct way to treat a particle quantum mechanically. We now know how to find the position, momentum, and energy of a quantum mechanical wave function. We now ask, how does the wave function evolve in time? Remember that the entire idea of quantum mechanics is to describe a particle as a wave. Therefore, if we want to know how the wave function of a particle evolves in time, Let's recall how a normal classical wave evolves in time. A monochromatic field has some complex amplitude phi that is a function of position, and a time-dependent part that evolves as e to the power minus I omega t. The time evolution of a polychromatic field is found by summing all the monochromatic fields together. Now comes the quantum mechanics. According to the Planck-Einstein relation, the angular frequency and the energy of a particle are related to each other. So, if we substitute omega by e over h bar, then we have the expression for how a quantum mechanical wave evolves in time. We can further rewrite the expression by recalling that the energies En are given by the eigenvalues of the Hamiltonian h, and the functions phi n are the eigenvectors of h. So we can apply h to psi, and write psi as the sum of monochromatic fields phi n. Because phi n are eigenfunctions with eigenvalues En, we can substitute h with En. The factor of En can also be obtained by taking the time derivative, and this derivative can be taken outside of the summation. The summation is the same as psi, so we now find the differential equation that describes the time evolution of a quantum mechanical wave function. This equation is known as the Schrodinger Equation. The eigenvalue equation that gives the energies and the energy states is also referred to as the time-independent Schrodinger Equation. We can draw an insightful analogy between the time-independent Schrodinger equation from quantum mechanics and the Helmholtz equation from classical optics. We can write down the time-independent Schrodinger equation and rearrange its terms. We can then write down the Helmholtz equation for a refractive index n that changes as a function of position, and we find that the two equations have the same structure. In both cases, the wave function phi is multiplied by a Laplacian plus some spatially varying function. So we can draw the following analogy. If light goes from a medium with a high refractive index, like glass, to a medium with a low refractive index, like air, then the field doesn't propagate in the second medium if the angle of incidence is higher than the critical angle. Instead, there is an evanescent field that decays exponentially. However, if there is a second medium with a high refractive index, then light can still propagate through the gap. This phenomenon is known as frustrated total internal reflection. To make the analogy with quantum mechanics, we can write the potential energy V in terms of the refractive index n to make the time-independent Schrodinger equation the same as the Helmholtz equation. We now see that the wave function can propagate through a potential energy barrier the same way that light can propagate across a gap of air between two glass blocks, even at an angle higher than the critical angle. In quantum mechanics, this phenomenon is known as quantum tunneling. Now let's summarize all that we have seen so far on basic quantum mechanics. The fundamental assumption is that we can describe the particle with a wave function. This wave function can be represented in different bases, for example, the position basis or the momentum basis. The squared modulus of such a function can be interpreted as a probability distribution according to Born's rule. A wave function with a definite position would be a delta function in the position basis, and because of the Breuil's relation, a wave function with a definite momentum would be a plane wave in the position basis. From these two observations, it follows that the position and momentum representations of the wave function are related by Fourier transform. Using properties of the Fourier transform, one can derive that an uncertainty relation holds between position and momentum, which is known as Heisenberg's uncertainty principle. Because in general a wave function doesn't have a single unambiguous position or momentum, these observables cannot be described by a single value. Rather, they become operators that can act on a wave function. If the wave function has a definite position, then applying the position operator to it simply multiplies the wave function with that position value. So mathematically speaking, states with a definite observable value are given by the eigenvectors of the observables operator, and the corresponding observables value is given by the eigenvalue of the operator. Since we know the eigenstates and eigenvalues of the position and momentum operators, we can derive that in the position representation, the position operator is a multiplication with x, and the momentum operator is a derivative with respect to x. One can straightforwardly check that these operators don't commute, and that their commutator is I h bar. We can find the allowed energies and their corresponding wave functions by finding the eigenvalues and eigenvectors of the energy operator, which is known as the Hamiltonian. According to the Planck-Einstein relation, These energies are related to angular frequencies, which describe the time evolution of each energy state. Using this property, one can derive the Schrodinger Equation, which is a differential equation that relates the Hamiltonian to the time evolution of the wave function. We know how to treat a particle quantum mechanically, but what we want to achieve in the end is to describe light quantum mechanically. We know that a monochromatic field oscillates harmonically, so let's study a harmonically oscillating particle using quantum mechanics, so that we can later use those results to quantize optical fields. Let's first recall how to treat the harmonic oscillator classically. We have some potential that is quadratic in x. By taking the derivative, we can calculate the force at x on the particle, which is in this case proportional to negative x. From Newton's second law, we know that this force determines the acceleration of the particle. By equating the two expressions for the force, we find a second-order differential equation for the position as a function of time. One solution is given by x of t equals cosine omega t, which describes a harmonic oscillation. From this we can also calculate the momentum of the particle as a function of time, which turns out to be proportional to sine omega t. What we can do next is to make these quantities dimensionless so that they can be compared to each other more easily. We can multiply x by some factor and p by some other factor so that we now have two quantities which are both dimensionless. We can now write them as the real part and imaginary part of a complex exponential, just like we could write a monochromatic optical field as a real part of a complex exponential. Since these two quantities are now dimensionless, we can conveniently plot them against each other in a phase-space picture. We find that as a function of time, the particle rotates in circles in phase space. Now let's turn to the quantum mechanical treatment. We saw previously that to understand the dynamics of a system quantum mechanically, we need to look at the energy operator, or the Hamiltonian, which is given by the sum of the potential and kinetic energy. We can plug in the expressions for the potential and kinetic energy, and then introduce the same dimensionless quantities we saw previously to end up with the fairly simple Hamiltonian. What we want to do next is to find the energy levels of the system, which are given by the eigenvalues of h. There are two ways to do this. One way is to substitute the x and p operators with their representations in the position basis, which transforms the eigenvalue equation into a differential equation that can be solved for psi of x under the condition that psi of x should be normalizable. The other approach, which is the one we will use, is to use ladder operators. We start with our Hamiltonian with dimensionless quantities. The trick is to try to factorize x squared plus p squared. If x and p were scalars, we could straightforwardly factorize the expression into x minus ip and x plus ip. However, x and p are not scalars, but operators that do not commute. Therefore, if we expand the product, the two cross terms do not cancel out. Rather, they can be rewritten as the commutator of x and p. From the canonical commutation relation, we can work out that the commutator of the dimensionless x and p is given by I over 2. We can plug this result into our equation, and then add 1/2 to both sides to find an expression for x squared plus p squared. If we then multiply both sides by h bar omega, we find a sort of factorized expression for the Hamiltonian. We can rewrite this expression further by introducing the ladder operators a and a dagger, which are also called the annihilation and creation operators for reasons that will become apparent in a minute. The dagger indicates the Hermitian conjugate of an operator. With these definitions, we can rewrite the Hamiltonian in terms of a and a dagger. Using the commutation relation between x and p and the definitions of a and a dagger, we can furthermore derive that the commutator of a and a dagger equals 1. With these results, we can demonstrate that the creation and annihilation operators respectively raise and lower the energy level of the system, hence their names. To see how this works, let's assume that phi n is a state with energy En. This means that phi n is an eigenvector of h with eigenvalue En. Using the commutation relation, one can then demonstrate that a times phi n is also an eigenvector of h with energy En minus h bar omega. In other words, applying the annihilation operator reduces the energy level of the system by h bar omega. Similarly, one can demonstrate that applying the creation operator increases the energy level of the system by h bar omega. It can be shown that by applying the creation and annihilation operators repeatedly, all energy levels of the quantum harmonic oscillator can be found. So if we plot the energy levels of the harmonic oscillator, we find that we can start at the lowest energy level, which is not 0 but 1/2 times h bar omega, and then we can go up in steps of h bar omega by repeatedly applying the creation operator. Notice that we're getting on the right track now. We saw that to explain the photoelectric effect, we assume that light comes in packets that have an energy of h bar omega. Since a classical electric field oscillates harmonically with frequency omega, we decided to look at the quantum harmonic oscillator, and indeed we found that the energy levels of the harmonic oscillator increase in steps of h bar omega. So in a sense, we can think of the harmonic oscillator as containing packets of energy of h bar omega, which can be created or annihilated with the creation and annihilation operators. Note that the number of packets, or quanta, correspond to the eigenvalues of the operator a dagger times a. Therefore, this operator is also referred to as the number operator, as it counts the number of energy packets that are present in the harmonic oscillator. So the results we found for the quantum harmonic oscillator seem plausible, but it's still not obvious how the quantum mechanical and the classical harmonic oscillator resemble each other. For example, we saw that classically the position and momentum of the particle oscillate harmonically and out of phase with each other, but where is the oscillatory motion in the quantum case? Classically, a particle has at each point in time a definite position x and a definite momentum p. Quantum mechanically, there is an uncertainty relation between the two. So to find the quantum state that most resembles the classical case, it makes sense to find the state for which the uncertainties in x and p are minimal and equal. Such quantum states are called coherent states. So let's see if we can find the quantum states that minimize the uncertainty in x and p. Let's start by recalling the uncertainty principle. It states that the standard deviation of x times the standard deviation of p must at least be h bar over 2. By squaring this inequality, we find that the product of the variances must be at least h bar squared over 4. If we consider the dimensionless quantities, we find that the product of their variances must be at least 1 over 16. If we want the uncertainties in x and p to be minimal and equal, we require that the variance in x must be 1 over 4 and the variance in p must also be 1 over 4. Now let's see how these variances depend on the quantum state psi. Recall that the variance of x is defined as the expectation value of the squared difference between x and its mean value. The expectation value of an arbitrary observable q is given by the integral of q times its probability function. According to Born's rule, the probability function of an observable is given by the squared modulus of the wave function in the basis of that observable. This squared modulus of the function can be written as that function times its complex conjugate. The multiplication with q can be obtained by applying the q operator to the wave function in the q basis. We can now rewrite the integral to find the identity operator, which we can leave out. We then find the simple but important result that the expectation value of an observable q is found by sandwiching the q operator between the bra and ket factors of the wave function. We can use this result to write the variances of x and p as a function of the wave function psi. So now we have obtained two equations using the variances of x and p. Using the commutation relation between x and p, we can write down a third equation. With these three equations, we will find the condition for psi to be a coherent state. So let's write down these three equations. We multiply the bottom equation with I, and then add the three equations together and expand the squares. Next, we're going to collect a bunch of terms and rewrite them in terms of creation and annihilation operators. First, we can write x squared plus ixp as x times a. Then we can write p squared minus ipx as minus ipa. We can combine these terms into a dagger a. Next, we can factorize the mean of x squared plus the mean of p squared so that we get the mean of a dagger times the mean of a. For the remaining terms, let's consider the expressions for a dagger times the mean of a, which we can write in terms of x and p and expand, and a times the mean of a dagger, for which we can do the same. If we add them, we get 2 times x times the mean of x plus 2 times p times the mean of p, which are exactly the two remaining terms in our equation. So we can substitute them to obtain an equation purely in terms of a dagger and a. We can further factorize this expression, and we find that some factor times its Hermitian conjugate equals 0. This means that the length of that vector is 0, which means that the vector itself must be the null vector. If we now rearrange the terms, we find an eigenvalue equation that says that A applied to psi must equal the mean value of A times psi. So in other words, a coherent state is an eigenstate of the annihilation operator, and its eigenvalue is the expectation value of A. We have found the condition for psi to be a coherent state. Now let's find out what the wave function of such a coherent state looks like as a function of position. First, for the ease of notation, it's common to call the expectation value of A alpha. Now recall the definitions of A and the dimensionless quantities x and p. If we use this to write A in terms of the usual x and p operators and substitute these with their position basis representations, we now find how the annihilation operator acts on a wave function psi of x. By plugging this into the eigenvalue equation for psi, we find the differential equation that needs to be solved. We can rearrange the terms of this equation and find that the solution is given by a Gaussian function which is shifted by alpha. Note that in general alpha can be complex valued, so let's write it as its real part plus its imaginary part. If we then expand the square, we find three terms. The first term is a quadratic term depending on x. The second term is a constant term independent of x. And the third term is a purely imaginary term depending on x. We can pull out the constant term and absorb it into the integration constant, since anyway the wave function must be normalized. Moreover, if we're interested in the probability distribution of x, which is given by the squared modulus of psi, then the imaginary part of the exponent becomes irrelevant, and we find that the probability distribution of x is given by a Gaussian that is shifted by the real part of alpha. And similarly, one can demonstrate the probability distribution of the momentum p is given by a Gaussian that is shifted by the imaginary part of alpha. So we have found that the coherent state, which is the most classical-like quantum state, is an eigenstate of the annihilation operator, which is a Gaussian wave packet in both the position and momentum representation. We wanted to see whether for these coherent states one could observe the same oscillatory motion one sees in a classical harmonic oscillator. So we must now look at the time evolution of the coherent state, which means we need to describe it in the energy basis. Recall that the energy levels of the quantum harmonic oscillator are spaced equally apart by h bar omega, and that one can go up or down these energy levels by applying the creation or annihilation operators. Let's denote the state of definite energy as n, where the number n indicates the number of energy quanta in the harmonic oscillator. These states are called Fock states, and they are eigenstates of the Hamiltonian and also eigenstates of the number operator with eigenvalue n. So if we calculate the expectation value of the number operator for an n-photon Fock state, we will of course find n. We can rewrite the expectation value of the number operator as the squared length of a times n, and we know that a times n is proportional to the n-1 Fock state. We can combine these two results to infer that the annihilation operator applied to an n-photon Fock state gives an n-1 photon Fock state multiplied by square root n. We now know that a coherent state is an eigenstate of the annihilation operator, and we now know how the annihilation operator acts on an energy state. So we can find an expression for the coherent state in the energy basis, which means we can calculate the time evolution of a coherent state. Let's write the coherent state as a linear combination of energy states, with coefficients that are to be determined. We can apply the annihilation operator to both sides of the equation, and we know that on the left-hand side it reduces to a multiplication with alpha, and on the right-hand side each n-photon Fock state becomes an n-1 photon Fock state multiplied by square root n. Because the n equals 0 term of the summation vanishes, we can start the summation at n equals 1. Now we can shift all indices from n to n plus 1 and start the summation from n equals 0 again. If we then divide both sides by alpha, we can compare this equation to the one above it and find the recursive relation that relates Cn plus 1 to Cn. If we write Cn plus 1 as a function of Cn, we can pick some arbitrary C0 and use the recursive relation to subsequently find C1, C2, etc. If we look at the expressions we get, we can come up with a formula that directly relates Cn to C0. We can plug this formula in the expression for the coherent state. Now all we need to do is to find C0, which is determined by the normalization condition. If we plug in the expression we found for the coherent state and recognize the summation as the Taylor expansion of the natural exponential function, then we find an expression for C0. And with this result, the expression for the coherent state in the energy basis is now complete. Note that the coefficients give a Poissonian probability distribution with a mean that is the squared modulus of alpha. With this expression for the coherent state in the energy basis, we can straightforwardly find the time evolution by multiplying each coefficient with a time-dependent complex exponential. We can plug in the expression for the energy and then simplify and rearrange some factors to eventually find that the time evolution of the coherent state is given by multiplying alpha with a time-dependent complex exponential. Now recall that the probability distributions of the position and momentum were Gaussians shifted by the real and imaginary part of alpha. This means that as a function of time, the probability distributions oscillate as a cosine and sine, just like a particle in a classical harmonic oscillator. We could describe the behavior of a classical particle as a point rotating in circles in phase space. For a coherent state, we could do the same, except the point now becomes a spread-out function because the probability distributions for x and p are Gaussian. The radius of the circle is given by the modulus of alpha, and the spread of the function is 1/2, due to Heisenberg's uncertainty principle. Just like in the classical state, this function rotates in circles with angular frequency omega. This plot is called the Wigner quasi-probability distribution. It is created using the probability distributions of x and p. However, it cannot be interpreted as an actual two-dimensional joint probability distribution, because in quantum mechanics you cannot measure position and momentum simultaneously, so you cannot assign a certain probability to a pair x and p. Another way to see why it cannot be an actual probability distribution is because for some quantum states the Wigner function has negative values, and it makes no sense to speak of a negative probability. Let's summarize what we have seen about the harmonic oscillator. In the classical case, we saw that the position and momentum oscillate harmonically and out of phase with each other. Quantum mechanically, we have to look at the energy operator, or Hamiltonian, which we can write either in terms of position and momentum, or in terms of the creation and annihilation operators. By analyzing this Hamiltonian, we saw that the energy levels of the harmonic oscillator are equally spaced by h bar omega. By applying the creation operator, you can move up one energy level, or create an energy quantum, and by applying the annihilation operator, you can move down one energy level, or destroy one energy quantum. The operator A dagger A is the number operator, which counts the number of quanta that are present in the oscillator. The quantum states that most resemble classical states are coherent states. These are states that have minimal and equal uncertainty in position and momentum. The probability distributions for x and p are Gaussians, and they oscillate harmonically and out of phase with each other, just like in the classical case. It can also be demonstrated that the coherent state is an eigenstate of the annihilation operator, and that the probability coefficients of the energy states follow a Poisson distribution. Now let's get back to our main question. How can we quantize the electromagnetic field? We know that classically a monochromatic field oscillates harmonically, and we just learned how to treat a particle in a harmonic oscillator quantum mechanically, so we should be able to guess how the electric field is quantized. To treat a particle quantum mechanically, we need to calculate its total energy, which for a harmonic oscillator is given by x squared plus p squared. So to quantize the electric field, we probably also have to look at its energy, which is proportional to the squared modulus of the complex field, which we can rewrite as the real part squared plus the imaginary part squared. Note that classically, the position and momentum oscillate harmonically and out of phase, just like the real part and imaginary part of the complex-valued electric field. For a particle, we could define the creation and annihilation operator as the position operator minus or plus I times the momentum operator. These operators could add or remove quanta of energy. Similarly then, the real part minus or plus I times the imaginary part of the complex-valued electric field should constitute operators that add quanta to or remove quanta from the electric field. Classically, these operators would correspond to the complex field and its complex conjugate. We could represent coherent states, which are the most classical-like quantum states, as a spot rotating in circles in the xp plane. By analogy then, we can represent the quantized electric field as a spot rotating in the plane defined by the real and imaginary part of the field. In general, if we have a scalar polychromatic classical real-valued field, we can write it as the sum of real parts of complex-valued monochromatic fields. We can write the real part of E as 1/2 times E plus its complex conjugate, and we can write this as two separate sums. We can then substitute omega with minus omega, so that both sums contain the same exponential e to the power minus I omega t. The first sum is overall positive frequencies, and the second sum is overall negative frequencies. We can then associate the positive frequency part, which contains the complex amplitudes E, with an annihilation operator, and we can associate the negative frequency part, which contains E conjugate, with the creation operator. Note the creation and annihilation operators we found previously were time independent, whereas these new field operators depend on position and time. To treat this in further detail, one would have to turn to quantum field theory, but that's beyond the scope of the current introduction. Also note that in this discussion we have for simplicity ignored polarization and the magnetic field. So we've seen that we can identify the complex valued field and its complex conjugate with the annihilation and creation operators. But how would that manifest itself in practice? Or in other words, how does it affect what we measure? In the end, a detector detects photons by absorbing them, one way or another, which means that in the electric field a photon is annihilated. The rate at which this happens is given by Fermi's golden rule. If the field starts in some initial state I, the rate at which it transitions to a final state F after photoannihilation is proportional to the matrix element WIF. Since we aren't interested in the final state F of the field, and we don't measure it, we find the total transition rate by summing over all final states. We can write out the squared modulus as the product with the complex conjugate. Now recall from earlier that the summation over the outer products of all F is equal to the identity operator, which means we can leave it out. What's left is the product of the creation operator with the annihilation operator, which is the same as the number operator, which counts the number of photons in the field. Recall that by sandwiching this operator between the Bra and Ket factors of the quantum state, we compute its expectation value. In other words, the photon absorption rate is proportional to the mean number of photons in the field. Classically, the annihilation operator corresponds to the complex valued field, and the creation operator corresponds to its complex conjugate. Their product gives the intensity, which makes sense. The rate at which we detect photons is related to the intensity that one would expect classically. We can now study the photon statistics. Let's say we have a photon detector, and we shine light on it so that it detects on average 10 photons per second. How many photons do we measure in a 1-second interval? Obviously, on average, that would be 10 photons because we just stated that. But one has to bear in mind that this is only an average number, and for each 1-second interval, the number of detected photons might be different. For example, we could detect 8 photons in the first 1-second interval, 5 photons in the second interval, 11 in the third, and so on. When taking the average of all these numbers, we expect to find approximately 10 photons per interval. What we can do now is plot a histogram of the photon statistics. So on the horizontal axis we can put the amount of photons detected in a 1-second interval, and on the vertical axis we can put how often we detect that amount, which we also call the frequency, and which is not to be confused with the optical frequency omega of the electric field. We will find a distribution that has its mean at 10 photons, but also has a certain spread caused by the random fluctuations. So what determines the photon statistics? What determines what this histogram will look like? We saw that the photon absorption rate at time t is proportional to the expectation value of the photon number at time t, and that we could find the classical equivalent by substituting the annihilation and creation operators with the complex field and its complex conjugate, the product of which gives the intensity. Now we're interested in the time interval tau between two photon detections. So we can ask, if at the time t a photon was absorbed, what is the absorption rate at t plus tau? If at time t a photon was absorbed, it means that the annihilation operator of time t was applied to the quantum state psi. If we now want to calculate the absorption rate at time t plus tau, we use the same formula for the photon absorption rate as used above. We have the quantum state and its Hermitian conjugate, and in between we put the number operator. The resulting quantity is called the second-order correlation function, which is evaluated at tau. We can again look at the classical analog, which is found by substituting the annihilation and creation operators with the complex-valued fields and their complex conjugates. We write the products as intensities and find that the classical analog is given by the intensity correlation. So we have a second-order correlation function G2 of tau that can be interpreted classically as the intensity correlation and quantum mechanically as the probability of having a certain time interval tau between photon detections. The classical intensity correlation we can write more explicitly as a correlation integral. Now we will study these quantities for three different types of light: coherent light, thermal light, and non-classical light, which can only be understood quantum mechanically. Fully coherent light is classically given by a monochromatic field and its intensity is constant in time. So the intensity correlation function will also be constant as a function of tau. Quantum mechanically, coherent light would be described by a coherent state, which is an eigenvector of the annihilation operator. So just like in the classical case, the value of G2 of tau is independent of tau. Recall that quantum mechanically, tau represents the interval between two photon detections. So we find that every interval tau between photons is equally likely to occur. This means that the photon detections are completely uncorrelated, so independent from each other, and such a process is described by a Poissonian distribution. One characteristic of the Poissonian distribution is that its variance, which is a measure for the spread of the histogram, is equal to its mean value. Now let's consider thermal light. For thermal light, the intensity can vary chaotically as a function of time. If we compute the correlation for different tau, we find that G2 of tau must peak at tau is equal to 0. This makes sense intuitively. The intensity at time t is more correlated with itself than with intensities at other times. How would we interpret this plot quantum mechanically? Quantum mechanically, G2 of tau represents the probability to observe a certain time interval tau between two photon detections. So if G peaks around tau equals 0, it means it is more likely to observe short intervals between photon detections than long intervals. So photons tend to bunch together, and indeed this phenomenon is called photon bunching. If we were to plot a histogram of photon counts, we would find it has a larger spread than the histogram for coherent light because the intensity fluctuates in time. This means that the variance is larger than the mean, so we call it a super-Poissonian distribution. Now let's look at non-classical states of light that can only be understood in the context of quantum mechanics. If we consider an arbitrary function I of t, then its correlation integral must always peak at tau equals 0. So a correlation function that has a dip at tau equals 0 would make no sense classically. But can we make sense of it using the quantum mechanical interpretation? In the quantum mechanical interpretation, a dip at tau equals 0 would mean that it is less likely to observe short intervals between photon detections. This is known as photon anti-bunching, and it would lead to a narrower photon count histogram compared to the coherent case, because the photons are detected at more regular intervals. Because the variance is in this case smaller than the mean, this is called a sub-Poissonian distribution. Let's summarize what we have seen for the three types of light. One way to distinguish them is by looking at the second-order correlation function G2 of tau, which classically describes intensity correlations. Another way is by looking at whether photon detections are uncorrelated, bunched, or anti-bunched. A third way is by looking at whether the photon statistics follow a Poissonian, super-Poissonian, or sub-Poissonian distribution. So now we know the theory behind quantized light and how this theory can explain certain experimental observations. But can we also use this new theory for practical applications? One important application is noise reduction. We've seen that if we measure photons at a certain rate, then for classical light, the variance in the number of photons that we detect in a certain interval is at least as large as the mean number of photons. So if n denotes the mean number of detected photons and delta n denotes the standard deviation, then delta n squared must be at least as large as n for classical light. And for coherent light, we have a Poissonian distribution, in which case the variance is equal to the mean. We can define the relative error as the standard deviation divided by the mean. We can then find that for Poisson noise the error decreases with the detected number of photons as 1 over square root n. Here's what it would look like in practice. Let's consider an ideal, noise-free interference pattern which consists of light and dark fringes that we theoretically expect to measure on a camera. Depending on the strength of the light source and the exposure time of the camera, we expect for each pixel a mean number of detected photons n. Now let's pick a very low exposure time, so that even at the pixels where the interference pattern is brightest, we only have a mean number of detected photons of 0.1. We find that the detected pattern is very noisy because we detect very few photons. If we increase the exposure time so that we measure more and more photons, we see that the relative error decreases and the interference pattern becomes clearer. So the quantization of light results in noise that is for classical light limited by 1 over square root n, which follows from the properties of the Poissonian distribution. However, we have seen that non-classical light can follow sub-Poissonian photon statistics with a lower variance, so can we beat this quantum noise limit using non-classical light? Recall that the electric field has some inherent uncertainty due to Heisenberg's uncertainty principle. A coherent state, which is a state that most resembles a classical state, has a minimal and equally distributed uncertainty. Now we want to decrease the uncertainty, but according to Heisenberg's uncertainty principle, if we want to decrease the uncertainty in one observable, we have to increase the uncertainty in another observable. If we do this, we get something that's called squeezed light. We could, for example, decrease the uncertainty in the phase and increase the uncertainty in the amplitude to get phase squeezed light, or do the opposite to get amplitude squeezed light. Just like a coherent state can be represented as a spot rotating in circles, squeezed states can be represented as ellipsoidal spots rotating in circles. The probability distribution of the real part of the field can be measured experimentally, which is evidence that these states indeed exist and can be generated. We saw that for classical light the error scales as 1 over square root n, so in principle we could make the error arbitrarily low by making n arbitrarily high. However, in practice it's not always possible to increase the laser power or exposure time by the required amount. In that case, squeezed light can help reduce the noise error while keeping n fixed. This technique is used in interferometers for the detection of gravitational waves. So in summary, to quantize the electric field, we have to interpret the complex field E as the annihilation operator and its complex conjugate as the creation operator. The classical intensity then corresponds to the number operator. With this, we can describe the photon detection process, and we can distinguish 3 types of light based on the photon statistics. For coherent light, the photon statistics follow a Poissonian distribution and the photon detections are uncorrelated. For thermal light, we have a super-Poissonian distribution and photons are bunched together. Non-classical light gives a sub-Poissonian distribution and photons anti-bunch. Because photon detection is a random process that follows at best a Poissonian distribution in the classical case, measurements are shot noise limited. This limit can be overcome using non-classical light, such as squeezed light.